When we observe a complex system in motion, the immediate activity often obscures the structural baseline it was built upon. We can track the precise speed of the changes, but we lose sight of the starting point. In calculus, differentiation is the specific mathematical tool used to isolate this behavior. It extracts a momentary rate of change from a system's total state. Look at these two distinct total functions, y equals x to the sixth plus 10, and y equals x to the sixth minus 50. If we differentiate both of them, the math forces them to converge into the exact same derivative output, 6x to the fifth. Notice what happened to those starting points. The positive 10 and the negative 50 are absolute constants. Because they have no inherent rate of change, differentiation removes them from the equation, reducing them to 0. Because the act of differentiation erases baseline data, reversing the process requires a specific mechanism to account for the information that was lost. This reversal process is called indefinite integration. Its primary objective is to take a differentiated rate of change and reconstruct the original equation, the primitive function or antiderivative. If we start with our derivative of 6x to the fifth and attempt to work backward, simple guessing might work for basic integers, but that method fails as system models become more complex. Instead, we apply formal notation. This elongated s is the integral sign, indicating the reverse operation, and the dx at the end is the explicit instruction to integrate with respect to the variable x. We define this result as indefinite because applying the integral without knowing the system's starting conditions yields an infinite family of potential functions rather than a single definitive answer. To resolve the math, we append a plus c to a reconstructed function. This is the constant of integration. It serves as the mandatory placeholder for whatever absolute numerical value was removed during the initial derivative. Indefinite integration establishes the mathematical necessity of identifying and accounting for unknown variables within any reconstructed model. Moving beyond simple integers requires a systematic set of mathematical rules to rebuild these equations. Look at this first formula, known as the power rule. It governs how to integrate any variable x raised to a power n. The mechanic works in two steps. First, add 1 to the existing exponent, and then divide the variable by that new sum. If we apply this to integrate x to the sixth, we add 1 to the power to get 7 and divide by that 7, resulting in 1/7 x to the seventh plus c. This specific rule holds true regardless of whether the initial power is a positive integer, a negative number, or a fraction. However, there is a mathematical failure point. If the exponent n equals -1, adding 1 results in an exponent of 0. This pushes a 0 into the denominator, creating a division by 0 error that breaks the equation. To handle this specific case, we use the logarithmic exception. Integrating 1 over x, which is identical to x to the negative first power, resolves to the natural logarithm of x plus c. These rules provide the algorithmic foundation required to reconstruct algebraic structures accurately. The third rule governs exponential functions, addressing equations where the variable itself is located in the exponent. For an exponential function like e to the power of mx, the integration mechanic requires you to divide the entire term by m, which is the coefficient of x. The fourth rule addresses how we handle complex equations with multiple terms, utilizing the sum, difference, and constant rules. Indefinite integrals function as linear operators. Distinct polynomial terms linked by addition or subtraction can be isolated and integrated independently. We can see this in a complex polynomial example, the integral of 2x squared minus 4x to the sixth. The integral operator and the dx instruction distribute directly to each individual term, allowing us to split the equation in half. Applying the power rule to the first term, we add 1 to the exponent of 2 and divide the existing coefficient by 3, giving us 2/3 x cubed. We repeat the same power rule isolation for the second term, which integrates to 4/7 x to the seventh. Finally, we combine the isolated terms back together. Because we are generating a single new function, we only need to append one constant of integration at the end. With these 4 rules established, analysts possess a complete mathematical toolkit capable of reversing multivariable systems back to their origins. When we apply this mathematical theory to economics, derivatives are identified as marginals and primitive functions as totals. A marginal value measures the incremental change resulting from producing or consuming one additional unit of a good. Our first application uses integration to reconstruct a total cost model from isolated marginal cost data. Marginal cost is the expense incurred by producing exactly one additional unit. Here we have a marginal cost rate of 3Q plus 10, with Q representing the quantity of units. To find the total, we set up the integration with respect to Q. Distributing the integral, the total cost function resolves to 3/2 Q squared plus 10Q plus C. In this business context, that plus C represents the company's fixed costs, which exist even if 0 units are produced. Here, those fixed costs equal 80. We can use the same logic to determine a total revenue model from marginal revenue. Marginal revenue is the additional income generated by the sale of one more unit. Look at a marginal revenue function of 80 minus 2Q. Integrating this rate yields a total revenue function of 80Q minus Q squared plus C. This resulting total revenue equation maps out the income ceiling for the firm across any volume of production. Because total revenue is price multiplied by quantity, we can divide this total aggregate function by Q to extract the underlying price equation, isolating P as 80 minus Q plus C. Abstract integration provides the mathematical framework required to build actionable macroeconomic baselines from isolated performance metrics. The final operational hurdle is moving from an indefinite family of functions to a single definitive equation. We achieve this by solving for that unknown constant. Consider rebuilding a total consumption function from the marginal propensity to consume. The MPC measures the proportion of any additional income that a consumer chooses to spend rather than save. Here, the rate is 0.3 plus 0.2y to the negative 1/2. We begin by setting up the integral with respect to y, representing total income. Applying the fractional power rule, the equation integrates to a total consumption function of 0.3y plus 0.4y to the 1/2 plus k. We substitute k here as our constant of integration. To lock in the value of k, we use boundary conditions. These are specific data points about the system's baseline state used to anchor it. For this economic model, our known boundary condition is that total consumption equals 90 when income is exactly 100. We substitute these boundary conditions directly into the integrated formula, replacing c with 90 and y with 100. Processing the basic algebra, the square root of 100 is 10, simplifying the right side of the equation to 30 plus 4 plus k. Solving for the constant gives us exactly 56. Plugging that value back in yields the finalized absolute of total consumption function. Indefinite integration functions as the critical mathematical mechanism for reconstructing the total economic structures that govern a system.